Hello everybody. Here I am with a new homework announcement. This will be the second homework in our lesson. Now, this is a similar case study as of the homework 1. We have an autonomous vehicle that is moving on its own, and we are given the acceleration dynamics. This means that we know what the relation between the acceleration reference and the acceleration is. We know the transfer function of those dynamics. Then we construct this speed loop and position loop, this structure here. Since we know the dynamics between the acceleration reference and the acceleration, if we add an integrator to our model, then we have the relation between the acceleration reference and the speed of the vehicle. Now, since we want to control the speed of the system, of the vehicle, we can construct this speed loop here, where we have a controller and a feedback, unit feedback in this case. At this point, if we apply a speed reference, the speed dynamics can be observed, and we can see if we are able to and how we are able to control the speed of the vehicle. Now, we can repeat this process in order to come up with the position control of this vehicle, this autonomous vehicle, by adding an integrator and then repeating the process here, having a unit feedback loop and a controller. So we apply a position reference here, and this will be this input, and the output, the measurement, will be used in order to generate a speed reference, and that speed reference is used by the next controller, and then we are producing an acceleration reference. This means that we are trying to adjust speed and acceleration so that we meet we are tracking the position in terms of input-output relations. Now, we have also a little bit information about the whole application here. We know that the vehicle has a certain limit to its acceleration-deceleration rate, namely 2 meters per second squared. And we have a speed limit that is 50 kilometers per hour. Now, it is also known that due to safety regulations, that the vehicle can only move forwards. So negative speed values are not allowed. So we're designing our controllers. Once we're satisfied with our controller synthesis, then we apply certain limits, because this is a real-world application inspired example, a case study. We know that the acceleration should be limited because we cannot infinitely accelerate, and you will see that hopefully if you look at that during your synthesis. Now, we can also not go up in speed to very high values. We have a limit here. So those limits are given. Negative speed is not allowed. And we should track, I'm speaking for the controllers here, we should track the acceleration reference and speed reference without overshoot. This is because of the limits. We have to obey them. So if we design a controller that does not overshoot, we are obeying the rules here. So the limits. We are trying to stay in the limits, between the limits. So that gives us the overshoot value that we are looking for, namely 0. But the time domain specifications, they are up to you. Those time domain specifications are settling time, peak time, rise time. We could have given you some settling time, peak time, rise time. But in this case, since we have some limitations, you will not be able to speed the controller and the closed loop dynamics as you wish. It will have a limit because we have a limit here in terms of saturation. So you will come up with a settling time, peak time, rise time, probably settling time. We will try a settling time value, and once you're done with that, if it's within the limits, you can use it. Limits being 50 kilometers per hour or 2 meter per second squared. So this is up to you, but you will need to try and validate and repeat that process. So using this figure, you're asked to design a PID controller for F1 here. So the first task is to use the system, use this integrator, use this whole model, and design a PID controller that does not overshoot if I apply a VREF here, a speed reference, and it should track the speed here. So first you will try this with the PID controller. Then the second task is to repeat this process with the PIPD controller, but in this case you can use the previous design in in A, where you had the PID design. So based on the existing PID controller, you will go ahead and try to come up with a PIPD controller here. So as usual, you are asked to provide the pole zero map, the unit step response, and the resulting transfer functions, the closed loop transfer function and the control transfer function. And also you should provide your design steps here. You should explain step by step on how you've chosen the parameters that are to be chosen here. Now, since we did design a controller that regulates the acceleration reference, or that generates the acceleration reference by looking at the speed reference and the speed and comparing them and using this measurement. Now we can repeat this process for the position loop. We can apply a position reference, we then have the position, and then the difference gives us the error, and then our controller takes action and generates a speed reference. Now we will design F2 as by using a PID controller, again pole zero map, unit step response, and all that stuff here that's written down. And then again we will ask you to come up with a PIPD controller based on the PID controller. You're free to redesign it, the PIPD controller. You don't have to use the PID controller that you've designed previously, but it may be a good idea to use the existing one. So up to you. Now, once you've solved A, B, C, and D, you are practically done with the control system design here, the controller synthesis here. Task E is about using those PIPD controllers and looking at the validation of this whole design. Now, you will apply this input here, 500 meters, and this autonomous vehicle should go 500 meters. But since there are limits, we should apply those speed limits, 0 and 50 kilometers per hour. This is VREF, and the same for the acceleration. Now, since you have an integrator and saturation, you will have a wind-up problem, and you should solve that with the anti-wind-up structure. Now, you're asked to plot the vehicle's position, speed, and acceleration signals in one plot. So acceleration and down to speed, then maybe the position. Yeah, you can just construct your plot as you wish. Now, since you have designed a PIPD controller, and since you have to add the anti-wind-up structures, you are asked to provide a detailed block diagram of the resulting control system, including those controllers and added structures. So detailed, and use the numbers there of F2 and F1 and G and 1 over S. You have to provide the whole picture here with the solution in it. So a detailed block diagram of the resulting control system. Now, let me remind you that we have to apply our limits to our references. If you, for some reason, add a saturation element here somewhere or here, what you're doing is you're misunderstanding or misinterpreting the output, because adding something to the output does not change the output, it just changes your interpretation. So the sensible thing here is to add those saturations to your control signals, since you are applying those signals. If you apply a limited signal, then that will take action. But if you limit the output, which is your measurement, that does not make sense. So please be careful where you add your saturations, but obviously you should not add them where X is or where the speed measurement takes place. So this is the explanation or and the extra information that I can provide you. Hope that it was useful, and hope that during this homework the learning and since this is a case study, the whole process will hopefully be fun for you. So good luck, and if you have any questions, feel free to ask them on Google Classroom, because that's, in my mind, the fastest way. So good luck.